Howdy.
Howdy.
It's our pleasure to have Dr. Andreas Tolk here. I met Andreas when I was attending this 2023 Winter Innovation Conference, and where I met with Andreas and heard about his work. So today we have a pleasure to get Andreas here to give a talk about merging agents, social science, and big data into artificial societies. So Dr. Andreas Tolk is a member of the Modeling and Analysis Innovation Center, which is a part of the MITRE laboratory, which some of you know it's started from a Lincoln lab from MIT. Before he joined MITRE, he was a professor of systems engineering at Dominion University, where his research focused on interoperability and composability of model data-driven solutions. So currently he is serving as a chair for the Society of Modeling and Simulation International. His research was recognized by distinguished contribution awards of the Association of Computing Machinery and the Society for Modeling and Simulation International. He published 15 textbooks and more than 250 book chapters. And he's a fellow of SCAs and a senior member of SAM and IEEE. So with any further ado, I just introduce, let's welcome Dr. Andreas Tolk for the talk.
So the translation of this wonderful resume is there's an old fart who is definitely not going to tell you something new, but is just trying to live from everything that he did over the last 25 years. I'm very happy to give the talk today. I'm a chief scientist for complex systems modeling, which means that I can take very simple systems and model them very complex, so that people give me some research money to tell them how to solve them better later on. The MITRE labs are modeled after the national labs. So the idea of MITRE is it's an organization that is running federally funded research and development centers, which is working on independently funded research in support of the government. And that also means that we work a lot with academics and we work a lot with universities. And so hopefully we're going to be able to work a lot with Texas A&M as well. In particular, as we have a lot of things in common, like we just talked about digital twins, and I'm going to talk a little bit about digital twins in this context here as well. But this is mostly based on bringing different ideas together from what I'm thinking about. So MITRE is supporting the whole thing, but this is not a MITRE talk. I'm working for MITRE, and my IP belongs to MITRE, no matter if they are paying for it or not. So that's why we have the MITRE copyright on it. But all this is cleared. You can utilize everything. The talk is going to be recorded. You can ask me for the slides. I gave a couple of papers to Gian to distribute when you go to the website to download them. So that's about me and about the introduction. What I want to do is I'm a little bit cheating here, because I really want you to understand the big context that data science is playing in this idea of artificial societies. So I have the introduction, understanding the problem is one bullet, but that is actually one of the main bullets of the talk. I'm going to spend some time on it to really create the idea of what do we want to accomplish when we are building these artificial societies, before we go into the technicalities about the way that we came to the artificial societies, what are the elements, and what particular can data science do to support this development of artificial societies. This is a talk, yes, but I know it's an ARE, it's an acronym-rich environment. So if I use any acronyms that you do not know, just ask. If there is anything in the slides you don't know, just ask. If there's anything in the slides you don't like, just tell me. So I like this way more to be more interactive. Otherwise, it's going to be expensive for the institute when they have to pay all for my drinks tonight to get my voice up and going again. So let's jump in. First, let's understanding why do we need way more simulation-based decision support today. How many of you are still in the undergrad education? I think everyone is a graduate, 100 good. So within undergraduate, you very, very likely are going to learn a lot about operational research and how to use linear algorithms, how you use gradient production systems, and other things to solve optimization problems. I borrowed this idea from Scott Page, who wrote the Model Thinker, and he said that is like you are in a landscape and you see the Fuji or the Kilimanjaro. They work perfectly well if you have this one optimum that is right here. So that is how we are preparing our students. We are still preparing our students like this. We are still teaching Hilly Lieberman 40-year-old optimum algorithms. And they have their place, they're good, they're all right. But they are not always applicable, in particular not when you come into the real world. When you come to the real world, suddenly your Mount Fuji looks like the Himalaya or the Alps or the Rocky Mountains. Your wonderful little algorithms that work so well here are starting to brittle and do not always lead to the right optimization challenge. And they are still relatively solid. Yes, over millions of years, Rocky Mountains and Himalaya are going to change, but if you have a solution today and you found out where Mount Everest is and the height is, it's going to stay stable for quite some time. But the more we are starting to look into the modern problems of today, where we are looking into computational social technical studies, we realize that it's not only bad that we have not one, but many different optima, but these optima are changing during our observation and during our optimization. So we have more this Centium problem, where the optima are shifting during space. One of the examples, I had the pleasure to lead the modeling and simulation effort during the COVID activities, where my corporation and the Maya Clinic organized a COVID healthcare coalition where we had 160 industry members all contributing. You all see the slides on the news at the time. That was typical of this problem, because the moment we identified what is good to help us to overcome the epidemic, we had to implement these interactions. The moment we implemented the interactions, we changed the system, because now our system was not the one that we observed, but the one that we observed with the pharmaceutical interventions, the non-pharmaceutical interventions, and so on. So by working with the system and optimizing the system, you're changing the system, and then you go back into the same circle again. And that is something which is known, but which is not yet as much surely supported as the traditional operational research algorithms that we have. What makes the whole thing worse is that we are very often dealing with deep uncertainty. Deep uncertainty can be translated into we do know nothing. The official part was introduced in a RAND report already a couple of years ago, 2003. And the idea was that you have a problem where the analyst cannot, so different groups cannot agree on what is the right concept. How do we describe this problem? It's weird, it's non-intangible. And even if you can describe it, you do not know what are the real characteristic parameters. And what are the real characteristic parameter values? What are the value ranges? And you have a lot of different opportunities to go to. So you can do a deep design where you do a full swipe, hopefully a little bit supported by things like genetic algorithms over the solution space to come up with an ensemble idea of simulation or computational support. But even if we find a solution, we not always can agree is this really is a desirable solution. So how to deal with this? That is a complete additional talk. The main idea is that you are focusing on the main identified alternatives that are identified by the social groups that is in charge of the whole thing. And there are a lot of good techniques out there, most of them heuristics. And there's a book, and this book is open access. It's on the website as well, dealing with a lot of very nicely summarized ideas how to overcome this. So, why do we deal with this? If it's so hard, if it is so complex, if it is so changing, we do not have the right algorithms to deal with it. First, it's a good place for a university because they are the smartest and brightest, so we should find and find solutions here. But there are also deeper social reasons why we do it. Nigel Gilbert is one of the leading computational social science members of the editorial board for the Journal for Artificial Societies and Social Simulation, and together with Petra Arweiler and a couple of additional experts in the field of policy support. He only recently wrote a paper on where we are regarding computational modeling in support of policy, and I really like his introduction. As I say, whenever there is a cost or a risk associated with the policy change, which is high, and the context itself is complex, so that people cannot simply by common sense find out how to deal with it. It's not only necessary, it would be unethical not to support the decision makers. And so it's within the ethics of the engineer to contribute as good as we can. And we ourselves in a little study where we looked into healthcare and applied some of our findings in the context of COVID research, we realized when we spoke with the decision makers all the way up to White House level that the real problem is that when the decision makers are under stress, they have to decide on something. They have to do something. And very often they just do something, reacting ad hoc, not planning in advance, but just acting on what's happening. And that is very often directly leading to treating the consequences and not the root problem. So instead of focusing on what really is the problem, what really needs to be addressed, we are treating the consequences, and that is a big challenge. And this is the problem of this complexity we talked a little bit earlier about. So there's the problem. Our policymakers need help. The world is very complex, and maybe just a little example. People always say, oh, the world was always complex. I grew up very often supporting the Department of Defense with Common Warning. And if you just look a couple of years back, we had the Army, we had the Navy, and we started to have something like the Air Force. And the domains were very clearly separated. The Army took care of the land part, the Navy of the sea part, the Air Force of the air part. But with all these developments over the recent years, we realized that this stovepipe organization is no longer working because our weapon systems, our sensors, our intelligence systems were all overlapping. And who is organizing what's happening in these overlapping areas? And these overlaps are growing more and more, so that by now, every piece of the battlefield can be addressed by every service that is available. And that is leading exactly to these complex situations where nobody knows what to do, and nobody knows who is in charge. And then there are different ways to solve the problem, and they are applicable in this context as well. So that's why we are seeing more and more complexity popping up, because it's not only happening on the battlefield, it's happening with contracts. Our contracts are all over the country, not only the United States, go into Southern America, go into China, go into Europe. And suddenly you have these overlapping things where you have nonlinear interactions, that are strongly overlapping, and you have a complex systems where your old ideas are no longer working. So you are reacting ad hoc, treating the consequence because you need to steer something. Don't just throw up your hands, Jesus sticks with it. So how do we want to do this? That's the last part, to understand where we are and what we need to do. We have lots of data. We started to have little data with COVID and got more and more and more, but overall we have really lots of data. And very often the challenge is that we have too much data and we do not know which data to use. Plus we have these challenges of things like complex, adapting to what we are doing while we are doing it, and we have deep uncertainty. And we want to support the understanding of policy effectiveness and alternatives. The good news is that there is something that has been developed decades ago in the system engineering approach. Russell Ackoff came up with the DIGWI pyramid. DIGWI stands for data, information, knowledge, wisdom. And the underlying idea is the following. Maybe there is a pointer then. Those on the following the screen, see it as well. We are starting with big data. And we have this data part, and what we do is with data modeling and data analytics, many of the things that you are learning here when you're learning data science. We are starting to recognize that there are common patterns, that there are correlations, that there are connections hidden within the data that is helping us to better understand the system that is described by the data. Now the rule comes in and we have to start again from the switch. So with this data modeling, we are now able to understand at least a little bit of a first connection and the first order of our systems. By recognizing these patterns in these data models, we are putting data into context, which makes this information. We can now take this information and can find out if these correlations actually have causal implications. There are a lot of correlations that have no causal implications, some very interesting ones. So if you have time, just Google correlations that have no causality implied. There are a couple of very nice correlations out there, like that the sweetness of California ice cream is totally correlated with the murder rate in Wisconsin. Nobody would assume any causality, but if we use neural networks, we have to be careful as our neural network can learn exactly this. So just on a sideline. And what we want to do instead of having this machine intelligence looking into all these elements, we would like to really understand what are our functions and embed them into simulations. Why simulations? Simulations are algorithmic. So we are putting knowledge plus data to create now our knowledge that can be further explored. So with our simulations, we now are able to look and understand the causality within the system as far as we know it. And we are able to describe the dynamics of the system. We can describe where are we and how did we get there. We can explore it furthermore and visualize it, making it immersive, so that decision makers, a good friend of mine from the Stevens Institute who recently retired, Bill Rose, he always said we need to develop something like a flight simulator for the decision maker, so that the decision maker can make his decision and sees the impact of the decision and feels them directly within the simulation. So you can use a big decision theater with lots of different displays or whatever you are interested in. This immersive visualization is important to give this feeling of there's something happening. And with this, we can now not only understand where are we and how did we get there, but we can start to put this by using deep design, going through all the different cuts of the hypercube and stability evaluations to understand what are our options, where can we go to, what are our, I always say here we have situation awareness. Here we have option awareness. Here we know where we are, and here we know what we can do. And this really helps then to come to the understanding, because we are bringing these different elements together. And the method that is currently looked at increasingly, in particular after successfully applied and utilized for the COVID evaluations, are these artificial societies. Very last thing, I love to work in cross-disciplinary teams. I always have worked in cross-disciplinary teams. Since when I started to work on my PhD, I was in a team where we had ecologists and policy scientists and computer scientists to build simulations, put them into context and so on. We are more and more required to put our different disciplines to work to solve a solution. And there are different ways to do so. Multidisciplinarity. What you do, you bring your experts together to solve one problem. The result of this is that they are coming up with some juxtaposing and sequencing, coordinating of their activities, and there are some ad hoc exchange of information happening, but you more or less are staying independent, and once the problem is solved, you break your team up and go away. Interdisciplinary is a little bit more, because now with inter, you are focusing on how do I solve a class of problems. I realize I always have certain problems in the inner structure of my city. No matter what city I'm looking at, it's always the same problems that are popping up. So I can build an interdisciplinary group that is looking at this particular problem. And what they normally do is that they are not only integrating their infrastructures for some data exchange, but that they are starting to bring in interoperability of implementations so that you can bring your systems together more closely. This is data science. This is data management, data replications, and data dynamics. And if you bring the minds together, that you realize it's actually not enough to work between the disciplines, but to create something which is transcending the old idea, which is creating something new, a new discipline. Then you are working in the transdisciplinary space. And here you are not only looking at the implementations, you're also looking at the conceptualizations. So, how do we support all this? And all this was the first bullet. Now we're going to see how we actually get there. One of the favorite solutions of the academic community is the use of the agent metaphor. Because it's pretty intuitive, it's people understand it quite well. What you have is you have an agent. This agent can communicate with other agents. He can perceive his environment, can act on the environment, can have, if you have an advanced agent, goals, beliefs, and desires, so that he is using these goals, beliefs, and desires to drive his action, can actually also drive his perception, but mostly his action and who he is communicating with and how he is building coalitions. And this perception is leading to a representation that then can be used for an internal simulation to come up what is the best way. And the representation and the perception that you see up there is not wrong. It's just incomplete, because this agent here seems not to care at all about triangles or the second tower. He may not be really interested in communicating. So his main goal is to get to the ball and get it somewhere. And you can now apply this in all the different ways that you say, I have different types of agents. I have homogeneous agents where all the agents are the same, or I have heterogeneous agents where I have two different sides. They can have the same structures, they can have different structure. All this is leading to multi-agent systems. multi-agent systems are a tool, not a solution. Multi-agent systems is a way we are thinking about the world using the agent method. So it provides, when it is well done, a heterogeneous agent population in their environments that can help you to better structure your system, understand your system, and actually introduce some first social components. The multi-agent system becomes an agent-based model if the model is applied to solve a problem. And this model is always a task-driven abstraction and simplification of the real system of interest, because you never can do anything, everything. You have to focus on what really is important for you. And that is leading to the challenge that we just saw on the last slide, or the slide before the last slide, that if you have two different disciplines, for them, different things are important. So you cannot just take this model and this model, plug them together and everything is fine, because the way the disciplines are thinking about the problem is different. So while they may use the same data foundation to work with, the interpretation of the data is different for each of the disciplines. And that is something data science has to understand, it has to support, it has to make sure that we are not combining apples with oranges when we are bringing these models together. But we have huge systems that are built up and that are starting to work and make their way into social science. And the other way around, unfortunately, when you are in the science family of engineering, most of them are focusing on the computational options and computational challenges. Here are two pioneers of agent-based models, George Epstein and Rob Axtell. They wrote a fantastic book in '96, How to Grow Artificial Societies, How to Build Social Sciences from the Bottom Up. The problem is that the subtitle could have been that computer scientists tell social scientists how to do their work. And that is never working well. Here is Nigel showing up again, Nigel Gilbert. He had a much better way to do this. And one of the activities that I had the pleasure to participate in was a collaboration with a group of humanists and computational social scientists that were looking how is it possible to better understand, with the mindset of a social scientist, social phenomena that are represented within computational methods, simulation, big data, machine learning, and so on. So they were looking into the possibility, how can we use the simulations and all the supporting activities, and how can we use data analytics to better understand how social networks emerge, how social networks drive human dynamics. Is the social network the driving force that helps the human to make decision? Or is the human decision the one that helps to set up the social network? So are you data scientists because you all belong to the college, or does the college get these special characteristics from all your contributions? Are the people who say that you are completely determined by the social networks correct? Or are the people who say, no, everything is driven by the individuals correct? The answer? I don't care. I can model both of them and then compare the results and check out which is there to better explain what's happening. And it always starts with data. So with computational social science, a lot is done by scraping online data, creating the networks to visualize them, and so on and so forth. And that was a book that I contributed to with a colleague of mine from the Virginia Modeling Analysis Simulation Center, who did a lot of the preparation of the simulations. Wesley Wildman is a professor for theology and also a professor for data science at the Boston University. He looked into the stability influences of reaction onto society using simulation system. Laurent Schulz is from Stavanger, but he was born here in Texas. And he is focusing on the same problem. And I helped to get the whole thing set up. And it was very interesting when we started to use the simulations, how people started to look into the visualization and how things worked. And we had this one group which was more on the atheistic side, being really convinced that the idea of theology is always going to be a dividing factor and is going to be a destabilizing factor in social groups, if not everyone is belonging to the same theology. And we had those that believed, Christians, Muslims, I think we had one Hindu, and they said, oh, that's not always the case. You always have to put the context in, and then you can find this more out. And then we had the simulation, and the simulation did run. This simulation was just the solution of a differential equation between point A and point B, nothing more. A differential equation connecting these two system states. The system state walked slowly into instability, and the atheists were starting screaming. We told you, we just increased the factor of religion, the societal structure is going to become a riddle. Here we have the proof. No, we don't have the proof, because nothing of what you just assumed is in the model. Nothing of this was in the data. So what you do is you make a hermeneutical mistake by looking at it, and you are interpreting your own biases and your own ideas into what you see on the screen. Then we went to the other side. Exactly the same thing happened. So that is where the data scientists have to say. One moment. Here is the data. Here's the correlation. Here's the causality. Your interpretation goes far beyond what we provided you. So be careful how to interpret the whole thing. Very fun-filled weekend, definitely. So, how can we try to make this better? Artificial societies, I always refer to them as agent-based models on steroids. Because what they do is, they have the individuals with their social parameters, with their health parameters, depending on what we are interested in. We can add more parameters, can take them away. And they are in a situated environment where their activities are constrained by the available resources, by available determinants, by physical constraints, and so on. If there's not a street between two cities, there's a hard way to get between. So we have these physical constraints. What makes artificial societies interesting is that we are explicitly modeling and simulating all the various social networks. Households, who are the families, workplaces, schools, where do you go, support groups, churches, and so on. And now it is possible that the individuals acting within the physical constraints, but their decision is influenced by the social networks that they are belonging to. And they can belong to several possible social networks. But their decisions always changes the overall structure of the social networks that they are in, because it becomes part of the social network structure. So the decision is no longer only driven by the physical constraints of the environment, but also by legal and social constraints that are given within the system. How does this look like when you're not only talking about it, but you're implementing it? That was our representation of Washington, D.C. regarding the representation originally of health factors, because we started to work on it in 2019, focusing on what is necessary to understand to better do anything against the opioid crisis. the opioid crisis started to sneak in for quite some time since 17, 18 and really became a problem. So at 19, we did build this system where we used huge synthetic representation, which is realistic but not real data, because if you have data about persons, you do not want to use the real healthcare data, and you do not want to use the real persons data. Otherwise, you don't want that someone goes into your simulation and finds out with what diseases, what illnesses is in what state and so on. But we also had a lot of survey and administrative data that helped us to create all this information, so that we are ended with 560,000 individuals in 260,000 households, with 200 schools and 50,000 workplaces. And we utilized artificial intelligence approach to scan through approximately 400,000 journal articles dealing with opioid crisis to come up with what are the internal states of our agents that are important for opioid evaluations, what are the likelihood of transition between these states, what are the external events, and how are these events related to events that we have in the society. Then they were represented accordingly. Then COVID hit. 2020, everything was shut down. And we looked at our model and said, oh, there really is a problem. Because when you look here, our social networks, they have a lot to do with support groups, helping churches and so on. And we saw here in our little agent that the likelihood from a tragic event to go into opioid misuse is way higher if you don't have the necessary support. And hindsight is 2020. Blinding flash of the obvious when you see, but what we said is, if our model is actually a little bit applicable, and we are looking at the non-pharmaceutical interventions to shut a lot of things down, including the support groups, including the churches, we will see a significant increase in opioid deaths. We did not quantify them. We did not say it's 50% more, 100% more. We just said it's going to be significant. We thought significant would be something like 80, maybe 90%. Reality proved us wrong. More than 200% increase in opioid deaths. And most of them because people did not get the necessary support, because they could not get in contact with the necessary support. And that's a typical example of one attribute optimization that does not take all these other concepts into account. Nobody wanted this to happen. But we were reacting, we were treating the consequences, we were going for doing something and not understanding the root problems that we have to deal with. Then Biden became president, and one of the first executive orders of President Biden was that every new law should be evaluated if it does not unproportionally affect minority groups. Very quickly thereafter was the quest, we have so many high water problems within the DC area. We need to increase the flood insurance. We have to restructure flood insurance. How do you evaluate if the change of the flood insurance is going to affect minority groups in DC unproportionately? Ta-da. What we did is we used a different set of information, brought all the house information in, used the traditional data of flooding and high water within DC, used the different models of how much of the insurance would be given over to the homeowners and how the insurance rates would increase based on this one. and who is going to be affected most. Again, it's not putting blame onto anyone, it's not putting guilt into anyone. It's just showing if you're serious about it. If you use this kind of structure, 80% of the burden is going to be carried by the ward number 8, which is one of the poorest wards within DC. Data science in the context, helping to make better policy decisions. Next step, what we want to do, and things that many of you are now used with the term digital twin, but you may not be aware that a digital twin is actually the end of a development of several steps. We are starting with a digital model. A digital model is a simulation system where you have the physical object and the digital object being connected via manual data flow. What we are trying to get to more and more is the digital shadow, where the digital object is following the developments of the physical model. And you look into your computer and you see what's going on, because whenever you changes in the physical objects, you update your digital object, but then you can still make your experiments here before you go back and influence the physical object. That's a shadow. See, the twin actually is originally understood that you have a direct, very tight coupling between the system and the digital system representing it. And changes in the digital system is immediately triggering automatic data flow to the physical object, like a control circuit that you see. How to use this for our artificial societies? There is a whole new series on research going on. Can we build a digital human twin? What can we do? How can we do it? I'm always a little bit iffy with the digital human twin. I think it will be a digital human shadow, because I don't want a simulation to directly inject something into my body. On the other hand side, when you think about space travel, and you have, or you think about a dangerous underwater activity, or you think about a soldier on the battlefield, and the sensor realizes there is a significant amount of blood loss, and we have to immediately do something to save the soldier's life. Or we have a significant decrease of oxygen, and we have to do something to save the astronauts. All these kinds of things. Or you have a casualty evacuation. Somebody is in, you have your little, I like your playground that you have here where you're blowing things up, and then have robots to get in and find out if they are able to get some casualty out in time. If this robot now has a nice physical representation of the human body, this robot may be able to do more than just extract. He may do triangulate, may be able to do first aid and so on. So there's hope, there are challenges, there are a lot of things to discuss in the community. Then what about our social nets? Can we build a digital twin of society? Should we build a digital twin of the society? Should it be just maybe a digital model, or at least a shadow? I would have loved to have a digital shadow of the society when COVID hit. We needed 3 months just to find out where we get all the data from. We got data in 25 different versions from 20 different organizations. And trying to align all of this to make this kind of understanding what's going on in the society was hard. The last one, I think, is absolutely trivial. We already use digital twins for everything. We have a digital twin for a bus, we have a digital twin for the public transportation, we have one for the infrastructure, we have smart buildings. Why do we let all the others play with these nice toys? Why don't we use them to create our situated environment to make sure that this really is top-notch and take care of all these different aspects, individuals, sort of net security environment to the degree we need it. Why do I say this here? It all starts with data. If we don't understand the data, if we don't understand the data correlations, if we don't understand how big data is contributing to make this being senseful, meaningful, we don't even have to start. Just to give you an idea, when we started with this, we had 169 census tracts in the 8 wards of the District of Columbia. So we were looking into approximately 5,000 different representations of households and schools and so on and so forth. We decided to go for synthetic data to generate the individuals. First, it was available. Second, we avoided all the legal problems that we can run into. We had a lot of additional data sources, and all this came with their own formats, their own interpretations. We had housing data. Unfortunately, the housing data that we got was limited to house ownership. We did not find any good data on renting. And house ownership and renting are very important because a lot of people that are affected by flood and by fire and by any other problems are not the people that own the house, but the people who rent the house. And then there is a question, what's happening if the homeowner gets a higher insurance rate? Is he going to just give it up over to the renters, or is there an alternative solution? So, let us know the challenges that go straight down your alley. Where I need your help, where I need your support to look for better solutions, because we found solutions, but many of them are ad hoc and need more research. Very simple is the geospatial discrepancies. We have the data of houses within DC from these 6 different sources. They result in very different city representations. So the same house is not at the same geospatial place. We have one where we have the representation where it uses the street address, the other one where it uses plot information, the other one where it uses geospatial representation, and they do not line up. So which one do we need? Which one do we use? Do we accept that there are discrepancies and we just say, if you are having this application in mind, you use the data representation from the group that is dealing with it, and that is this representation of the geospatial representation. But what if this is now triggering an event for a different discipline? We don't know. We have different resolutions. And here my warning, resolution doesn't equal equality. You can have a very high resolution, which is crap. And you can have a very low resolution, which is high fidelity. But we have to deal with it. One data source is going down to the individual, others are just looking into the population of a building, population of a school. With different scope. So what I take to be characteristic is not given in another solution. With different structure, because every discipline is dealing with the problem differently. With different accuracy and precision. Which means accuracy, how close are we to the target, precision, how well are we with being able to repeat this. So if you look at the 2 principles, this one close to the target. This one is highly repeatable. That's the difference between accuracy and precision. So if I know that I'm highly precise but I'm not accurate, I may be able to find something to counteract. Problem is this, are we counteracting the right thing? Or are we reflecting our own bias? Reliability, pedigree, age of data. We have lots of metadata that we very rarely took into account. So one of my favorites is this one. Coming from the DoD perspective, my customers are often have an absolute fetish for reality. When we do a combat simulation, they want to know, can this simulation replicate exactly this battle in history? Which it seems to be okay on the first look. But think about this, our observations are just one instantiation of a distribution of possible events. What happens if the first shot is not hitting the commander, but is going somewhere into the grass and the battle is completely different? Each battle is one representation, one instantiation of possible outcomes. So when we are looking into this, we should think about how likely, where does this observation fall into the possible distributions? Fun part, most of these important events only happen once. You cannot, in the battle, say, stop, freeze, everyone back onto the original positions, we are going to run the battle a second time. To a certain degree, you can do this with maneuvers, and we do this here in our center from Texas A&M. They have the possibility to run a lot of replications to get a good idea. But for the really big things, move it. Swine flu. Do we want to go for it again, trying something new? I don't. So how do we support the better analytics by taking this into account? Then everybody's talking about big data. What we realized is that we need a lot of data imputation. Data imputation from statistics, you are representing data that you don't have with a good assumption. So, example, we have data sources for the house owners. The data sources provide the expected insurance premium, but many houses are rented. So what is this going to mean? Tailoring data. What do we do if our structures are not safe? What do we do if our alignment doesn't work? What do we do? Can we use geo-information data? Can we use subject matter estimates? And how does this influence the overall simulation preciseness and accuracy? And reliability and fidelity regarding supporting good methods. And the bad word with V. Verification, validation. And the more we are dealing with digital twins and with mechanical engineering, uncertainty quantification. How do we know that what we know is the right thing we know, that is correctly modeled, that we are aware of what can go wrong? What are the various things that are triggering a need to look into this again? And this goes back to research gaps for future directions for digital twins, where people looked at it the moment that we have changes in our data collection process or the noise of data, or we are adding or deleting data sources, we have to go back into the validation verification process. The moment our distribution of the data that is shared with the artificial society or the other way around is changing, we have to redo our validation verification process. And the nice thing is that we do not even have a really good definition of what validation and verification means in this context. So lots of PhD topics coming out of here. To wrap things up, it's always good to learn to crawl before you walk, before you dance. So we have a lot of experience with scoreboards, dashboards, and so on, where we are capturing what happened and who was engaged. That are these factual informations, there are spotlights. Then when we add the when and where, we are creating time series that actually happened in the spatial analysis. When we want to address the why, that's where it really starts to become hard, because that is a correlation analysis and that requires a lot of additional research. How do we capture this? I'm a big fan of using ontological structures to do so. An ontology is in principally not much more than a good modeling effort with lots of additional logic and assumption and constraints. If you start, this is a colleague of mine, Leo always came up with this ontological spectrum. If syntactical interoperability is enough for you, that you just have to know that you have the right structures to expose the database or XML, is fine. You just use the schema or syntax to capture it. If you want to make sure that your structure works, you need something like thesaurus, the lexicon. When you're starting to move to the research description framework schema tasks, which is starting to bring you up to semantic interoperability. Then you use description logic, resulting in OWL conceptual models. And then you are finally coming up with ontological representations on things like the sumo ontology, the suggested Abermafildi ontology, where you have this possibility that you have at least a common understanding between all the disciplines from which the discipline ontologies can be derived. But what is the logical level, the ontological level that really is needed to support our analysis? I don't know. So, and we have 3 minutes for 5 questions. Good. I think 5 questions for you. So how do I ensure that I observe and collect the right data under deep uncertainty? How do you do it? I don't know, that's why I have the question. Because if it's deep uncertain, I think I would just grab everything I have and collect it and then do a lot of curation and go for it. But that leads to the question, how do we provide trustworthy decision support, and actually what is establishing trustworthiness in our solutions? Yeah, we can do validation verification, but we don't know how to do validation verification. So do we continue to observe and put this in connection with the reality and observations? Maybe one thing, but that's a huge NSF grant just to get money to collect the data. There's no real theory behind it that I'm aware of. Then one of the big questions is always what happens with the bias in our data. If you look into the machine learning algorithms, I saw a nice meme the other day, which says you are never asking a lady for her real age, a gentleman for his real income, or a machine learning expert for his data. So how do we overcome this? Just talked about data curation. Is actually data curation possible without knowing the application domain of the collected data in detail? And if we know it, are we not introducing additional bias when we do so? I love statistics. A little bit awkward when it comes to this. But I'm always amused when I see statisticians when they have their distribution. So let me try. I think I should be able to. So we have all our observations of reality. And the good statistician says, hey, that looks great. You see, here is my bell curve. And that's an outlier. Is it an outlier? Or is it a rare event? Is it an event that is of highest interest to us, but that is only happening so so rarely that it does not fit with all the other things, that we actually may have two distributions, one with the bell curve and one that explains the outlier. How do we ever get to this outlier if we throw it away? We are throwing way too much data away. And then last but not least, are there use cases where the synthetic data is preferable to real data? What is the role of the data scientist in these cases? Are you as data scientists as important for synthetic data as for real world observations? Are you more important? Are you less important? Do we need synthetic data scientists to deal with this? Because we are going to use more and more and more synthetic data. NASA is thinking about creating a lunar city and fly to the Mars. We need lots of digital twin information to support them. How to build the lunar city? Do we have enough energy? How is a society going to react if they are on very small spaces with very limited resources for 3 weeks or 4 weeks or 4 months if they are living in this lunar city? If you are flying up to the Mars, did anybody see the latest collection of reliable data about this information? There isn't. So do we just come up with synthetic data, or do we use data scientific principles? Which ones? I don't know. The NASA Advanced Research Project proposals are open in June. So maybe if you have an idea, that would be something to think about. And with this, I thank you for attention, participation, and hope that at least I was able to bring up some ideas to think about in the future when you work on PhD topics or research topics or work for NASA or NSF. Thank you.